Welcome to session number 6. In the previous session, we started our discussion on the laws of manufacturing, and we looked what is the process. So we have some input, and that process will convert that input to an output. And then there are some process parameters like inventory, mainly the work in process, the throughput, the rate at which the output is made, we call it R, and the cycle time, clock time taken in the process, right? So we also discussed Little's law, which connect these three parameters, and we said that how much is the minimum inventory needed to maintain a throughput rate of T for a given cycle time, right? So if for some reason or some way you actually can reduce this um, cycle time, right, T, in that case, there is a possibility you actually can reduce the inventory also. We have looked through an example, right? So we looked at an example where if we have the inventory lower than what is actually needed, then the system or the process may starve, right? And you may not sustain that throughput rate, right? So this is what we know as the Little's law, and as I mentioned in the previous session, that it's a folk law. Little only provide the proof for it, right? In 1961. So the connected to this law is another law which we know as the Kingsman's Law. I'm calling it a law, but normally it is in the textbooks. If you see, it is called as Kingsman's formula. It was given by JFC Kingman in the paper "The Single Server Queue in Heavy Traffic," published in Mathematical Proceedings of the Cambridge Philosophical Society. I think it came in 1961 again, and you can actually see something that both these papers were submitted in a span of about 2 weeks to two different journals, right? So, two important results more or less were derived simultaneously. And in this case, what we actually see are the three things. One is utilization, the other is cycle time, and the third one is variability, right? So you have a given capacity, and there is a utilization of that capacity, right? So it can vary from 0 to 100%. And then the relationship or the law gives you what is the impact of that utilization on the cycle time, and the third thing which comes is the variability, right? So you can actually see that the, the utilization, even for a given utilization, right? If the variability increases, the cycle time increases, correct? And this variability could be for the processing time at a machine, or it could be even the arrival, correct? So it's not necessary that all the jobs have to come at the in some kind of a so the jobs can be randomly arriving for processing, and then there would be a random processing time, right? So this variability will impact the cycle time for a given utilization, right? And you can actually see that this actually increases exponentially, right? After, so in this case, even if the variability may be moderate, and for higher utilization, the cycle time increases exponentially even for moderate variability, correct? Right? So this actually uh, mathematically gives us the wisdom, that old wisdom that variability inhibits speed, right? So if higher the variability, the cycle time would be higher and the speed would be lower, right? So the objective of that faster may not be achieved, right? So this gives you an idea. So one way, so in fact, when we talk about a typical manufacturing system, the utilization rates normally are higher, right? And if you actually combine it with higher variability, the cycle time rises exponentially, right? So one way out is either reduce the utilization or reduce the variability, right? And we will actually see that how you actually can reduce variability. So will there be some laws again which will actually come for our rescue to actually reduce that variability, right? So we'll talk about that because one of the things which we are going to talk is about the aggregation phenomena, how aggregation reduces variability, right? So is it possible for us to actually find some kind of an aggregation strategy which allows us to reduce the variability to improve the cycle time? So this wisdom from Kingsman's law is actually very relevant because the main idea of variability inhibits speed comes in the form of a mathematical relationship. So if you actually see the mathematical relationship in this paper, you can easily make out that the wisdom comes in this form, right? So we are looking only at the pictorial part of it, but the mathematical part is actually there in the, you can even check some of the textbooks, right? So with this wisdom, I'll go further and something which again some of you might have seen in the form of what we call as EOQ, the economic order quantity, but I want to relate it uh, this whole idea of economic order quantity with economic lot sizing, and we want to actually see what is the impact of the setup time on the inventory, correct? So this again relates to what we have said earlier, but let us just see what is the wisdom which comes out of it, right? So the story goes like this, that you actually have a setup cost which is given by S, and then there is a cost of carrying the inventory, right? So which is given by capital H, right? And what we want is we want to minimize the total cost, correct? Now in this case, if you see, we are saying that if the setup cost is high, you actually go for something called as a batch, right? So order or production in response to the high setup cost is called a batch. And the average inventory which arises because of this batching is called as a cycle inventory, right? And now there is a trade-off that there is a cost of carrying this inventory, which is H, right? So if you have high inventory, you actually incur that cost of H, and then there is a setup cost. So I can actually say setup cost could be like the setup time, right? Now we make that assumption that this R, which is the same as the throughput rate, is the steady outflow rate per unit time, correct? So that is something which we actually have to maintain, right? So it's a steady rate which is to be maintained, and then assume Q is the batch size, right? Now how you compute this total cost, right? So you can actually see that if we have to maintain um, the throughput rate and Q is the batch size, right? So R by Q is the number of setups, correct? Right? Because you are maintaining that throughput rate of R, and Q is the batch size. So R by Q is the number of setups which are needed, right? And every time whenever you set up, there is a setup cost which is S. So S into R by Q, right? Now, if you have a batch of size Q, in this case, because it's the steady rate, the average inventory would be Q by 2, right, at a given point of time because it's steady falling, right? And so you go to Q and then you consume R, then again you go to Q, and then so it becomes like a so the average inventory is Q by 2, and you multiply it by the inventory cost, right? So that becomes the total cost. And now if you do some bit of optimization, what you actually observe is that the optimal batch size, right, should be the square root of 2 into S into R by H, right? So this gives some kind of a relationship between the different costs, right? So if H increases, you can actually see if my inventory cost is high, I want a smaller batch, right? If my setup cost is high, I want a larger batch, correct? Now, this idea of setup cost you can relate to between the Ford and the Toyota examples. So when we were in the classical mass production setting, the setup time was very high, and you actually were looking for larger batches, right? So in fact, you actually went to an extent where you don't want any variety at all, because you don't want to switch from one product line to the one product line to the other product line, correct? Now, so you can actually see that, right? So when S is higher, your batch would be higher, and I bar in this case is the average inventory, that would also go up because that's Q by 2, right? And if inventory increases, the using the Little's law, even the cycle time would actually go up, right? Correct. So this relationship, if you start thinking, so one way is actually to reduce the setup time. So if the setup time goes down, the queue would actually be lower, the inventory would be lower. I think all that wisdom, whatever we have seen till now, actually can be evident from this formula, right? So how to reduce that as? Maybe you actually have to think about uh, the way the Toyota production system did that, right? So they do a lot of machining part, right? To reduce this, so you derive different kind of dies. So you look for the whole backup which comes along with that, right? So the machine tools improves, and you actually can reduce this setup time, right? And that will impact your batch size also. Now, in this case, right, you can actually see that, in fact, we have taken this path, but if the setup time actually reduces, the cycle time also will reduce. If the cycle time reduces, the inventory will also reduce, right? So we already have discussed that part earlier. Now, one thing which you can actually see that Q star is proportional to root of S. It is not proportional to S, right? Q star is also proportional to root of R, correct? And inversely proportional to H, right? So let us stop here. Now, one thing which comes very evident is that if R increases by say ninefold, let us just make some number, or fourfold, right? The Q star would increase only by say 3 times or 2 times. So for ninefold, it would be only 3 times, and for fourfold, it will be only twice, correct? Right? So if assume that for some reason my throughput actually increases by 9 times, the batch size is not linearly increasing, it just is a square root of that, correct? And this part would become relevant when we talk about the economies of scale. So there are scale effects in this particular setting, that if R increases, the throughput increases by 9 times, the Q star does not increases by 9 times, it just increased by 3 times, right? So it means that that gives you an idea about what. So assume that I am running 9 different plants, right? Now, or nine parallel lines, right? So if each is producing something, right? The Q star would not increase. So from 1, if I increase it to 9, the Q star would only go up by 3 times. It will not increase by 9 times, right? So this wisdom is important because what it actually says is it's about the economies of scale. We are going to talk about that, right? So I'll continue. And so next thing which, as I mentioned, that we have to look into what economies of scale mean. But before that, we have to define what's is a technology and what's a production function, right? So technology normally is defined in the form of a production function, and what is shown in this particular figure is that you actually have a set of inputs, which is y1 to yn, right? And you have a production function which takes all these inputs and gives you output, which is x, correct? And this is so you can actually say this could be, so it's only shown in two-dimensional, but this could be a n-dimensional figure, right? And you can actually see that so it's possible to use the inferior technology and maybe you produce something which is lower than what is actually possible, right? Correct. But in this case, we may be using the best technology, and given this input, this is the output we get. right, which is Fy or Fy1 to Yn, right, correct. Now, the point here is if you find a better technology than this, you may actually have a better production function, right? So you can actually see that instead of move point here, right? So one of the pursuits of the science and technology is to actually find better and better technology, right? So this is how it is mapped, correct? That we keep on looking for a better and better frontier, right? So we keep on going. So for the given input, and when I say technology, it includes all the processes which comes along with it. So it's not necessary the technology innovation has to be in only in the form of maybe the engineering side. It may be just a process innovation also, correct? So if you just look at this particular thing, that gives me an idea what actually is technology and what's a production function, right? So technology means that we are defining it in the form of a production function, which takes different inputs and gives me an output, correct? And in fact, I forgot to mention that this is also called, this whole shaded area is called as the production set. It means that that is something which is feasible for the given inputs, right? So I can always use maybe an inefficient process. Even the technology is very good, but I may not hit this, I may hit something here, correct? So the point here is we want to use the inputs efficiently and optimally so we can actually hit the frontier, right, for the given available technology, correct. Now, this particular notion of production function is actually used to define what economies of scale mean, correct, right? Now, if you look at on the slide, you can actually see that we have defined three things: increasing returns to scale, decreasing, and the constant returns to scale, right? And F is the same production function, right? So if you just look at the increasing returns to scale, in fact, I can actually call it the economies of scale, right? So it actually captures the scale effect part. So A is some parameter, and we assume that for all or for each A greater than 1, right? When I scale my inputs by A times, right? So earlier I assuming maybe using say 1 unit of each one of them, and now I am just multiplying each by 2, right? So I'm using 2 units of each, right? The output what comes of the technology or the production function is actually more than A times what I was getting earlier, right? So it is evident that when I scale it up by a factor which is more than 1, the output actually improves by more than that factor, right? So f of A in this case could be 2, 3, whatever, A of y1 to A of yn, that is actually larger than A times of what I was getting earlier, right? So there are benefits of scaling up, and that is where we call it increasing returns to scale or economies of scale, correct? Now the same logic is applicable when we say we have decreasing returns to scale, or in economics we call it diseconomies of scale, right? So there is a cost of increasing the scale, correct? And then there is a constant returns to scale when we say that, so in this case, just look at this. So A is not more than 1, it is greater than 0. It does not matter whether we scale up or not. What we get is just the same thing, right? So F times of A of A y1 to A yn is nothing but is just equal to A times of F. So what we were getting earlier multiplied by A. So there are no benefits of scaling up. So we call it the constant returns to scale. And you already have seen right from the beginning of this particular course what benefits this economies of scale actually brings in manufacturing, right? So with this basic definition, I continue more into the economies of scale. We already have seen a total cost function in the form of the EOQ, right? Now, for a given output X, there would be some total cost function given as X, right? So what is the average cost? Average cost is nothing but given as total cost by X, right? Correct. So you can even think of, say, total cost would be some fixed cost plus. Now, what is the average cost in this case? Is nothing but something like this, right? In fact, you can actually see that if X increases, the average cost is decreasing, right? That's a very important result because it means that there is a fixed cost capital K and then there could be variable cost small k, right? And that fixed cost is actually getting distributed for how much you are actually producing, right? So the larger the X, the lower is the average cost, correct? And this idea of lowering average cost or decreasing average cost is actually related to the economies of scale or increasing returns to scale, right? So you can actually see that for each X and A greater than 1, the average cost of AX is actually lower than average cost of X, right? So it means that when I scale the things up, the average cost is actually decreasing. In fact, this formula also does for this total cost function also is doing the same thing. So a firm with increasing returns to scale, we are calling it has a non-increasing average cost function, correct? Right. So this becomes uh, something which is relevant because if I have to say plot a function like this, it looks something like this, right? So you can actually see that as x increases, the average cost is decreasing, and that relates to the idea of economies of scale, right? Now, the things which when we talk about economies of scale, it's a relevant idea for manufacturing. But one thing which comes critical is it's a very mysterious concept, right? So it's not necessary. It will be so we still don't know why we observe the economies of scale, right? So there could be multiple theories around it. Right? So it's not, you can even not just pinpoint to one of these things, right? So in fact, sometimes people say that even the experience curve is actually bringing the economies of a scale, right? But actually these two concepts are different, right? So when we talk about economies of a scale, the experience curve is an independent concept. And that is where I think we mentioned about that. When we were talking about the bullwhip effect, we said that, or yeah, if when we were talking about the outsourcing, we mentioned about that when we outsource something, right, the cost at the supplier end would actually be lower because of economies of scale and the experience curve, correct? So, but for time being, let us just look at three different possibilities which brings these economies of scale. One is the classical volume effects, right? It means that when you have more larger scale, you actually would have more volumes, right? The utilization actually improves, correct? And that would actually lower the cost, correct? Right? And the main idea which we already have seen in the previous example that the fixed cost will be distributed, that also comes along with the volume effect. Now there could be capacity effects also, right? And we already have seen that in the context of the EOQ, right? It means that when I scale the things up in say from say 1 to 9, the batch size, the Q star does not increase in the same form, right? So my throughput may be increasing 9 folds, but my say inventory will not go up by 9 folds. I need much lower inventory, right? So in fact, this idea can be related. So if an organization has say nine uh, retail outlets, right? The centralized procurement would actually bring efficiency because if they order independently, so the ordering cost may not be distributed, right? Now, if you actually bring all these plants together and look for centralized procurement, the 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 transportation cost or the ordering cost will actually be distributed among these nine. Correct. So that is something which is the scale effect. Correct. Right. So the main point is that we are still saying that economies of scale is something which we observe, but we have not fully understood it because there could be multiple effects which gives what is that economies of scale or what we know as the economies of scale, right? So I just conclude this particular part with the learning curve. When we say that the total cost in this case, it's not just a function of what is the output, it is also a function of uh, how much we have produced earlier, right? So you can actually see that if we have produced some capital X units earlier, right? So that is the experience which comes by producing something earlier. So if X increases, the total cost function decreases, right? So total cost is not just a function of how much output I am producing now, it is also a function of what is the learning which has come in the previous production cycles, right? So that is captured by that capital X. So if capital X increases, the total cost decreases, right? So with this, we'll go further. So economies of scale, we are concluding with this. But I just gives you before I go to economies of scope. So these are some examples. I think we already have talked about the steel production, right? In fact, right from the ancient times, the scale effects were always there in the steel production, right? So a typical blast furnace. We already talked about the logistics side, right? The box, and you might have heard about very large crude oil containers, right? VLCCs, and they actually exhibit a lot of economies of scale, right? And I think some of you maybe you can find out there is a concept called as natural monopolies, right? Which actually means that even for very large uh, production uh, uh, quantity, the average cost will always be decreasing, right? So you always have economies of scale. You don't have diseconomies of scale for a very, very large quantity, right? So classical examples are uh, electricity or water distribution, right? So in those cases, it is always optimal to have just one firm in that market rather than multiple firms because of the economies of scale, right? And that is where we call it so natural monopolies. So it is by design that you just want one firm operating in a given market, right? So with this, we'll go to the so yeah. So one more example. I think we talked about that VLCC, so very large crude carrier, and this particular thing actually has happened recently in Chennai, and you can actually see that there. So this particular idea that you can actually bring the crude oil using this VLCC, right? It is saving Chennai port could save about 20 million US dollars per year by directly unloading from these VLCCs, right? So this is something of an scale effect because of large your cost is actually coming down. So large is beautiful. That concept is still valid, right? So I think with this, I will close this particular session. We will go to the next one when we talk about economies of scope, and we'll start discussing about the business models, right? Thank you.